Good day everyone. This is Rahul Deharkar from Mechanical Engineering Department, School of Technology, Pandit Deendayal Petroleum University. We are here for the online teaching courses for first year students. The topic of today's lecture is second law of thermodynamics. To begin with, I would like to start the revision of the few topics that we have already covered. So you must be aware of systems and surroundings, state, point and equilibrium, point function and path functions, heat and work sign conventions. These were taught in the previous lectures. Moving on, TV curve for the phase change of water was also a part of chapter 3. I would like to reiterate the TV curve since it would be useful for this particular chapter. So in this one, what we have was we had taken an experiment in which there was a cylinder with the area of, let's say, small a. In this cylinder we had put certain amount of water, and top of that we had put a piston with the weight W. So what we wanted to do was we wanted to plot temperature and specific volume curve with specific volume on the x-axis. Now what is the specific volume? The specific volume is nothing but volume divided by mass, and therefore the unit is meter cube per kg. And for our case it is nothing but area into height. Height would be the water column height divided by the mass, and on the x-axis we had specific volume, and therefore on the y-axis we have temperature. So to begin with, initially we are at a certain point where the temperature is T1 and the specific volume is V1. At this point what we look at, the entirety of this section is as a compressed liquid. It is called as compressed liquid. Okay, and at the same point I would like you to pay attention towards the pressure which is acting upon this particular liquid section. So the pressure on this liquid section would be given as atmospheric pressure plus the pressure of the, due to the weight of this piston, which will be weight divided by area. So total pressure would be pressure of the atmosphere plus pressure due to the weight of the piston. So now to begin with the experiment, what we are going to do is we are going to heat it up. So as we are starting to heat it up, we find that the temperature of this particular liquid will rise, whereas the specific volume will not show a tremendous amount of increase. There will be an increase, but it will be a ever so slight increase. So we will find something like this. The point will be raised little bit higher. So this will continue unless a specific temperature T2 is reached. So what is this temperature? What is the specific nature of this condition is, at this particular point the liquid is called as saturated liquid. What is the meaning of saturated liquid? I hope you are aware of the word saturated. So basically at this point the phase change process will start. Okay, so even a little bit amount of extra energy is given to this particular liquid section, the process of phase change will begin. So when the process of phase change begins, what happens is the amount of energy that you are giving to the system will be towards the phase change of the process and not towards the increase in the temperature. Therefore at this particular point T2, which is again also called as saturation temperature for the given pressure, we will find that if we continue to give the energy, the volume is increased whereas the temperature is remaining same, calling as the saturation temperature. So as we move ahead, we find that we will reach to a certain point where the bubble formation, or basically the steam formation out of the water, is happening, and we will see a mixture of steam and water. So if we continue to do it, what will happen is entirety of the water will be evaporated and only steam will be appearing. So that can be denoted by a certain point this. So a point where complete section of this complete liquid section is converted into steam is called as saturated vapor. So right now what points we have? We have saturated liquid and saturated vapor. Along with that, the central point or any point in between this line is a mixture, and the initial point was our compressed liquid. So even further, if we continue to give the energy, what happens is we see increase in the volume, and also the temperature is increased. So that can be shown by something like this. Okay, I would like to note that this particular representation is obviously not to scale, so this is for just representation purpose. So while this is happening, let's look at the points that we had. We had initially compressed liquid point, we had saturated vapor liquid point, then we had mixture point, which is anywhere between these 2 points. We had saturated vapor point, and we had superheated point. Okay, that is the name given to all these points. But the good thing that we have to look here is what happened to the pressure. This was the pressure which was continuously acting on the system, and throughout the entire experiment never once was this pressure disturbed. So basically meaning that if I draw a line joining all these points, what will I get is a constant pressure line. So basically all this during entirety of this process, the pressure never changed. So again, if I want to redo the experiment, but now I would like to increase the weight of this piston, so inherently increasing the pressure, so what will I get is I will get a curve something like this. So the upward shift is due to the increase in the pressure. Similarly, you will get a downward shift if there is a decrease in the pressure. So for now, let's look at what will happen if the pressure is increased. If I continue to increase the pressure, what we are seeing here is that the saturated liquid and saturated vapor points are converging towards one another. And now for if I join all the saturated liquid line points and saturated vapor lines, I will get a certain curve like this. So to look at this particular curve, let's look at properly. What we have here is this particular saturated liquid line is formed because of joining all the saturated liquid points, and similarly we have saturated vapor line which is formed by joining all the saturated vapor line. Now due to this particular line, the entire area is divided into zones. One of the zone is compressed liquid. So this particular zone is compressed liquid, where the liquid section where the experimental section or the fluid section is in the liquid format. Another section is superheated steam. So entirety of this zone is called as superheated steam, where the the test section was in the complete superheated form, right? And in between we have the liquid plus vapor mixture, where we will see water plus steam together. So this is the three sections that we had, and you had already studied about. So moving further, we also see that these 2 points converge together and we get a critical point. So what is the critical point? Critical point is the point where the saturated vapor point, saturated liquid line, liquid point and saturated vapor point is merging towards one another. So moving ahead, this is the actual TV curve for water. Let's look at all the sections that we have studied. This is taken from a online source, from the references given below. So what we have here is we have this dome. The dome that we see is because of joining all the saturated liquid points and saturated vapor points. So we can see saturated liquid line showing in this section and saturated vapor line here. Also we see the critical point. These blue colored lines are the pressure lines. So we have the superheated region, we have compressed liquid region, and we have the region where there is mixture. And you can see 1 megapascal pressure and increase in the pressure is 10 megapascal. So the increase in the pressure is shown upwards. So this was particularly taught to you in the previous chapters, and a few more things that was taught is how to get the values. The values meaning what are the properties of any given state. We have multiple states during this line. At any given state, what are the properties of this particular liquid? So since we have the 3 sections, let's start with that. One of the first section is saturated zone. Saturated zone means the mixture zone, which is denoted inside the curve, and there is a mixture of steam and water. So what we find is we have table A4 and A5, and in table A4 and A5 we see that the table A4 is saturated water temperature table, and A5 is saturated water pressure table. In both we have specific volume, internal energy, enthalpy and entropy. And how to find the particular properties? We'll require either pressure or temperature. Since we had seen in the previous one, in the dome section, the constant temperature line and constant pressure line are coinciding. Therefore either pressure or temperature is required. So what we have is, for a given temperature we will have a saturation pressure, and for a saturation pressure we will have a for a given pressure we will have a saturation temperature. So for any given point we will get two different points, which is Vf and Vg. Now Vf is the properties of the point at saturated liquid, and Vg is the properties of the point at saturated vapor. Similarly, it is for Uf, Ug, HF and Hg. So because of that, one more element is added to this particular system, which is called as quality of steam. Now what is quality of steam? It is nothing but mass of vapor divided by the total mass, which indicates that the value of X would be varying from only 0 to 1. 0 indicating there is no vapor mass, and 1 indicating that the entirety is vapor. So therefore, if X value is for any given X value, you can use this formula for any of this property, which will be UF plus X Ug plus Uf, which is sometimes written as UFG. So this was already discussed in the classroom. Moving further, we have superheated. So in superheated, we have to go to table A6, and there what we'll find is we have temperature ranging from 50 to 1300 degrees Celsius, and we have different pressures. So here we will require both temperature and pressure. For any given temperature and any given pressure, we'll be able to find the values. And for a value in between this particular 600 or 700, if the temperature is given 650, then obviously we'll have to do linear interpolation. The same is the case for compressed liquid water. So here also we'll find the similar pattern like the superheated one. The table number is A7. Here also temperature and pressure is required, and linear interpolation would be required in certain cases. So we had already gone through this. The few more things that we have discussed was ideal gas equation, PV and RT, and we had also discussed whether a steam can be called as ideal gas and at what condition steam can be called as ideal gas. We had also discussed thermodynamic processes. So thermodynamic process I would like to just give a brief on. We have pressure versus volume, and this is constant pressure process, and we have constant volume process, constant temperature process, also called as isothermal process, and polytropic processes. Apart from this, we had also studied what is work equations for the various process, and this is nothing but the area under PV curve. So a summary of this complete section is given here, where we find constant pressure process, which is also called as isobaric process, and the polytropic index of 0. The work equation is nothing but P delta V, which is given by P V2 minus V1. For similarly for constant volume process, which is called as isochoric process, the work is 0, and remaining all the processes is written here. This is obtained by the simple integration of this curve, which is obtained in the PV diagram. So moving further, what we have here is, in the last chapter that we have just studied through the online learning only, we had a certain numerical. This numerical was about mass or conservation of mass. So here what we had was, we had a tank. So here I would like to just take a while and revisit the video if you want to follow it up, that what calculations were done. So here I just want to show you what more you can do, and I encourage you guys to explore softwares like Matlab, Excel, to go through and develop your own understanding. So I will show you what you can do with this. So what we have in this experiment, what we have in this numerical is, we had a tank which was given certain diameter, and the liquid, which is basically water, which was given at H0, and there was a small opening which was having a certain diameter, dz was given, and you were asked to find out how much time will it require to have, like, for the water to reduce its level from H0 to H2, right? And I hope you had remembered the process. But here what I have done is, I have made a Matlab code which was able to solve this. Sorry for that. Matlab code was able to solve this, and I came up with such a certain type of GUI in which we can do the same. Okay, so this is the Matlab GUI that you can see. So here what we have is tank diameter 0.914. It is all the units are in our SI units, and all the data is already fed. So if I start the option, what you are getting here is the plot. This plot is time with respect to height of the fluid. So initially what we see that the height was reducing at a faster rate, whereas as you see, as the height is reducing from the water column, you see that the the time required for the reduction in height is increased. This is naturally visible in our day-to-day life. If you just practically see such such a tank, which will be simply called as emptying a tank, what will you find out is that initially the water level will decrease faster, but later on the slope will be flattening out. So here also we are seeing the same structure. So what will happen is this slope will continue until the height is reached 0. So the x-axis giving you the time, and y-axis is giving you the height of the fluid tank. So I think the calculation is done. So here also you can see, I think it was asked around 0.6, and the 0.6, if you just correlate it, is around somewhere around 700. So I think it will match your answer. And obviously you can play with this by changing the case. Let's take few examples. 0.1, liquid initial height of 1 meter, outlet of 0.001, mass in flow rate. Okay, this is something which was not given in the in that particular numerical, and I have added. Inlet mass flow rate was 0. So basically meaning was there was no addition of the mass to the system, so obviously it was 0. I will keep it 0, and t is nothing but the time step of how much it is increasing. So let's just look at what is the change of all the variables. Okay, so I'm starting it. So here you will see what is happening is around 40 seconds will be required for such conditions. Now we will see what happens if one parameter is getting changed. So here you can pause the video to assume or make your own hypothesis that what would happen. So first thing is, what would happen if I reduce the diameter of the tank? So earlier we took 40 seconds, now we have assumption of the assumption. So we are tank diameter is reduced, and let me just plot it, and here you can see a very different result. What we are finding here is that if the tank diameter is halved from the previous one, the time required is just 10 seconds, almost around 10 seconds. Okay, so that was something interesting. And let's say that the diameter is increased, then it was taken 0.2, so obviously we should see increases. We'll see what is happening. Okay, so here also we can see the curve is similar. We'll see a increase, a very high rate of discharge of water initially, but as the height is reduced, the rate of discharge will flatten out. And if we just increase the diameter of the tank, will be the time required will also be increased. So why this is happening, I leave it to you, and you can write about that in the comments, or you can just message it to me. So we are going back. So what will happen if the liquid height is increased or decreased? So also I think it is much easier for you to understand now. If I reduce the height, the time required would be low, and if I increase the height, the time required would be higher, right? That is true. Now what would happen with the diameter? Obviously if I increase or decrease, the time required would be less or more. So here the interesting point that I would like your attention is, what would happen if I increase, or sorry, basically not decrease but only increase the mass flow rate. Okay, so let's resume it and let's start it. Okay, so here we had around 60 seconds. Why it is 60? Okay, this is supposed to be 1. Okay, so it should be around 40. Yeah, so let's just take a scenario where I'm slightly increasing 0.01. So what is happening right now is, as you can see, it is kg per second. So with putting the value of 0.01 kg per second, it is indicating that externally I am putting water, a certain source of water, into the system or into the tank. So what we have studied in the previous chapter, that in the mass conservation, that if mass is coming in and if the mass coming in and mass going out is equal, then the rate of change of mass in the system will remain same. So in our case, if this is going to happen, then what we should be able to see is that the flow rate or the height of the water level should remain same. Now the question is, will it remain same, yes or no? So I would like to start here. So here we are seeing it is going to 0, so which indicates to me that the mass out was higher than the inlet flow rate. Let me just increase to 0.05. hopefully we will be able to see something else. So we are able to see something. Okay, so here we got something other, and what is written here, that inlet mass flow rate is equal to outlet mass flow rate. So and there, thus the water level is maintained constant. So here we are able to see it is not 0, it is just above 0, and that is where the height would be maintained constant, and it will continue to remain constant. In the code I have given it a certain criteria, therefore it stops the calculation and give me this dialog box. So similarly, if I just keep on increasing this particular mass flow rate, I will be able to get, so here it is around 0.1 or sorry 0.01 or something. So if I increase the mass flow rate, I should be able to see that the height maintained is higher. Eventually if I just increase it to a much higher value, what we'll see that the height, rather than decreasing, it will increase, but still we'll see the same thing. As there is an increase in the height, the discharge rate is also increasing. If you remember the equations, the discharge rate was the function of height of the water column. As the height is increased, we will also see an increase in the discharge rate, and therefore at a certain height we will see that the mass flow rate in and mass flow rate out will become constant, and therefore the water level will become constant at around, this is around 8.2 or 3. Okay, so I will give this, it will be provided to you and you can just do with your own, and I encourage all the students to do such practice with Matlab or Excel for all the numericals that you are learning, and therefore you will get a better understanding of the subject and the topic also. So moving ahead, let's start with the second law of thermodynamics. You can take a 5 minutes break if you want, but I will be continuing here. So what we are here looking here is that let's talk about the objectives. So in objective we have, first we'll try to talk about what is introduce the second law. We will also be able to see identifying the valid processes which satisfy both first and second law. We will also be able to discuss the thermal energy reservoirs, reversible, irreversible processes, heat engines, refrigerators and heat pump, and we will also be describing Kelvin, Planck and Cauchy statement of the second law of thermodynamics. We'll also discuss the concept of perpetual motion machines, and also lastly we will be able to apply the second law of thermodynamics to cycle and cyclic devices. Okay, so having said these objectives, let's start our idea. I think the spelling is wrong, Thougst. Okay, thought. Yeah, I think spelling is wrong here also. Fine. Okay, here it was correct. Fine, let's continue. Yeah, so thought bubble. So here I want you to imagine certain scenarios. So one of the imagining scenario is this is nothing but an engine. So what do we have in an engine? So basically if you think about it, what do we get out of an engine? What we get is output. What is the output? Is motion or work. That is something useful for us. Okay, and how do we get it? We get it because we provide some energy input which is in the form of fuel. Okay, so basically what we are doing, we are giving it energy and it is giving us output, work. Similarly, is it there losses? Any losses are happening during this process? You can think about it. Okay, so this losses is simpler. You can assume it like that whenever a engine is running, you will see that it is getting heated up. So that heat energy is nothing but the losses that we are seeing. So basically it will look something like this, that when an engine is running, we will take certain energy from the fuel which will be converting into certain amount of work, and we will also be releasing some amount of heat energy. Okay, so here I would like to like you guys to remember certain thing. So our source is some higher temperature source, and we are also losing to a certain losing our energy to the surrounding. We will call it sink. Just remember these two words, we will be using this later. Okay, so source is where we are taking energy and sink is where we are given the energy. Now the question here is, what is the efficiency of this particular engine, right? And also the question for any engineer is, what is the maximum possible efficiency for this particular system? So these are our thought bubble. This is something that we need to discuss upon and we need to work out. Similarly, I have a certain example for you. Let's take a case of a fridge. Okay, that is a fridge, and again I request you to take some time. You can pause the video and you can think about what are the systems or what we get similar to our engine that we had taken in the previous slide. Here what is going to happen? Okay, so I will continue. So what happens in a refrigerator is, actually electricity is given as an input, yes, and that electricity helps us provide cooling effect. Okay, So cooling effect, we had studied first law. We know that cooling effect is possible only when we take a certain heat out of it, right? So we have that. And also we will find that refrigerator is losing heat to the surrounding. And if you had seen any refrigerator, if you go to the back side of this refrigerator, you will feel warm. That is where the heat is lost to the surrounding. So if I want to put the arrows here, what I get is that cooling effect is taken from where we are losing the energy, and this black box indicate that cooling effect is not open to the system. Not open meaning that the cooling effect is happening only to a small box within which the cooling is happening. So basically meaning the entire area of the refrigerator is the closed area into which the cooling is happening, and it is not happening to the entire room which it is kept in. Okay, so in order for it to cool, what we have to do is we have to take energy out of it, right? And electricity, and that energy is given to the surrounding, okay, released into the surrounding, and this is done with the help of electric input. So this was the thought bubble. You will be remembering this, you had seen this, and this is something we observe in day-to-day life. Okay, the actual mechanism behind this we will be studying in this section itself. Okay, so here also I can ask the same question: what is the efficiency of this refrigerator, and what is the maximal possible efficiency of this refrigerator? So thinking about the efficiency, somebody can ask the question, okay sir, what is the meaning of 100% efficient system? So what is the meaning of 100% efficient system? Means whatever energy that I took is completely converted into the useful work that I need. Okay, so that is where perpetual motion machines comes into play. I will talk about a simple example. This is the example. Just take a case of this kind of example. Here you will see that a bulb is run via two solar panels. Those solar panels are using the energy of this bulb, and they are charging, or they are running this bulb itself. So theoretically speaking, if all the energy of this bulb is going to this particular panels, and this panel is able to develop into particular work, they should be able to run the engine, run the, what we can say, particular system. So this is something that will continuously, if working, if it is working, then it will continuously work. But obviously this is not possible. We'll discuss that in much detail. So here I would like to talk about that. I am providing you one such example, that there is a, okay, I'm not able to open it. Okay, sorry. Okay, so I have a small video that I am asking you to find. It is because it is by it is intended, why don't perpetual motion machines work? I request you to follow this video, and there you will see a very good examples on how or what the perpetual machines are, and why it doesn't develop. And obviously it is based on the energy required. The explanation is far well. I request you to also go ahead and observe this when this video is over. So continuing with this, we'll talk about it when the time comes. Okay, so moving ahead, so we have so much thought bubble thinking going on. Let's talk about it. We had first is the heat engine, right? We had so many things to discuss here now. So how much energy is going, what is source, how much output is going, what will be the efficiency, what will be the maximum possible efficiency, and we have fridge. So today we will try to discuss about the heat engine aspect of it. Okay, and the perpetual motion machine and refrigerator will be in the second video. So let's start with the introduction of the second law. So the statement is such that the second law of thermodynamics states that the state of entropy of the entire universe as an isolated system will always increase over time. So it is also, which is the meaning is that the change in the entropy in the universe can never be negative. So in layman term, what does it mean? So it means that along with the quantity, basically quantity means how much amount of energy. The first law talks about only about the quantity, key the energy can neither be created nor be destroyed, and it can only be transferred from one point to another. So we have total energy remaining same, but here we are talking about the direction of the process, that they are telling that the entropy will always increase. So just telling that there is a certain direction, there is a one-way process, that the process is always occur in a certain direction. Okay, and along with the second law we can understand that for any process to occur there are two difficulties that it has to come through, that is first law and second law. So all the processes must follow first law and second law in order to operate. So that means that the process has to satisfy these two laws. So let's look at certain examples that how first law certain processes can what we can say can follow first law, why, and cannot follow second law. So one of the best example here is a cup of hot coffee. So if you have a hot coffee, what will happen, and if you are keeping it in a room temperature of just room temperature and you are a hot coffee, what will happen is that the temperature of this coffee will decrease, but you will never find it that if you keep this particular hot coffee in the colder environment, that the energy from the colder environment is taken into the hot coffee and the temperature of the hot coffee is increased. That is not something you will ever find. Whereas if you try to do as per the first law, that should be possible, because whatever energy from the surrounding we are giving should be able to increase, but that is something which never occurs. It is always one directional, that the hot coffee will always go and become cool while releasing the energy to the surrounding. Another example is something like this. Electrical students will be understanding this very easily, that when we pass electricity through a wire, there is heat formation, but opposite is never true, that if we give the heat to a single piece of wire, then obviously we will not see an electricity to be generated. So basically it tells us that these processes cannot occur even though they are not in the violation of the first law. If you try to put the first law, that will be holding true, but whereas this is something which we never see in day-to-day life, meaning that it is, and also as per the given statement of the second law, it is obviously not following the second law. Moving ahead, what will be the use of this particular second law? As we had seen from the certain examples, we know that second law will be used to identify the direction for any given process. With the help of second law, we will be able to identify in what direction the process is going to move forward. This also gives us that talks about the quality of the energy along with the quantity. Okay, then another thing that we are also find is what will be the theoretical limits. Basically I had asked you in the thought bubble, what is the maximum possible efficiency, right? So second law will help us determining that in the cases like heat engines and refrigerators. So we are going to follow heat engine example right now. Okay, so moving ahead, this is the same thought bubble idea that we had, heat engine. So in heat engine, what we know is heat is getting in and system is working. So if you look at it closely, what is happening here is we have certain fuel which is burned, and that burning we can call it at a high temperature source, and from that we are getting the energy and it is going towards as the output as motion, and we are losing certain energy to the surrounding. Now just I will again ask a question to all my viewers, that is it possible that when an engine is running, obviously the engine is going to get heated up, but because of that heating up of the engine, does the temperature of the entire atmosphere will change? The answer is simple yes or no. So you can think about it, whether because of a certain heat engine and which is losing its energy to the atmosphere, will the temperature of the atmosphere change because of this? You can take your time to think about it, but the answer is no. It will be simply to give a simple example, let's take ocean, and in ocean if I say that a small droplet of hot water if I am putting, will I be able to see that the entire ocean's temperature is increased? Obviously no. So that is the meaning of a thermal energy reservoirs. So that is what we are going to talk about. Okay, so basically any thermal energy reservoir is nothing but a hypothetical body with relatively large thermal energy capacity, okay, that can supply or absorb finite amount of heat without undergoing any change in its temperature. So basically, as I explained just now, our atmosphere and or our oceans can be considered as thermal energy reservoirs. Okay, so which is the second line here also. In practice, large bodies such as ocean, lakes, rivers will be called as thermal energy reservoirs, but it is not limited to a large bodies. Okay, so I would like to point out that it is relative. So in this statement you can see a body does not actually have to be very large to be considered reservoir. So how it is possible? So you can see the second sentence, it says any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbs can be modeled as one. So basically, of any body which is having a certain amount of thermal capacity, but the amount of heat which is it is absorbed or released is lower, is comparatively lower without, and which is having no effect on the overall heat capacity or the overall temperature of the system, that system can be called as a thermal reservoir. To give an example, industrial furnace. So obviously furnace is not as big as ocean or atmosphere, but however we see that the temperature of the furnace is able to supply large quantity of thermal energy, and that too in an isothermal manner. Isothermal means that the temperature of the furnace is never decreasing. So this can be termed as a what we can say thermal energy reservoir. Obviously we will have to continuously supply fuel to maintain that maintain the temperature of the furnace, but the idea here is that the temperature of this particular source will never be decreasing. Okay, so that is the case. So heat reservoirs is basically can be termed into two different things. Here again two words are coming into play, which is source and sink. So basically source is nothing but any heat reservoirs from which we take energy, and when we take the energy there is no change in the temperature of that particular reservoir. Similarly goes for the sink, and sink is something which absorbs the heat without having a change in its temperature, which can be shown in this diagram itself. A source supply energy in form of heat and the sink absorbs it. Okay, so that is nothing but our source and sink. So moving on, heat engines. So what is an heat engine? So heat engine is now the device that convert heat to work. It is just exact same thing that I talked about in our thought bubble for heat engine. Let's look at it. First thing, they receive heat from a high temperature source. We had just talked about it. In our case it was fuel, and which was burning and providing us the high temperature source, and a part of it is getting converted heat to work. In our case it was the motion of the wheels that we are getting, or the shaft that it is rotated in the engine. Third is they reject the remaining waste to the low temperature sink, that also we had seen. Okay, the fourth point is something that we had not touched, that is they operate on a cycle. Now heat, if you look at the following line, it says heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called working fluid. Okay, so we are now talking about a cycle. So this is something that we need to look on, and it will be taught in the upcoming slides. So let's look at heat engine. So again I will just go back up and wrap this up. So we have heat energy input. So here fuel combustion takes place and provides energy. So this now can be considered as a high temperature source, and then we are losing energy, and this nothing but engine heats up and this energy is discarded to the surrounding. So our surroundings temperature is not increased, and we can consider it as a low temperature sink. And while this is happening, we know that the motion which we are getting by the virtue of the rotation of the wheels, that is a useful work. So basically this is an example, a simple example of heat engine. So heat engines now is shown in a representation view. In any books that you will find, you will see that the heat engine is shown something like this, where heat high temperature source is given as a cloud, and there the heat taken from it is given as Q in, and heat engine is always in this circular format. We'll talk about it what it is. And here we see that certain amount of energy is going to actual useful work, and the remaining is going to the sink, which is going as Q out. So looking at this itself, I can simply say Q in is nothing but summation of W net plus Q out. Okay, so here I have a question for you. So here what I am showing is I am going to draw this into three different sections. This can be represented in three different ways, and here also you can take some time to think about which of this is the correct one, 2 or 3. You can take your time, you can pause the video, but I will proceed with the explanation. So let's look at it. So while drawing, you will see you will draw something like this. What we are showing is source, sink, but now what I have done is a box I have made for the representing source and sink. And I hope you remember in the thought bubble I have made similar such box for representing fridge, where I had seen that the small container is where the heat was taken, and that is where we see a change in temperature. So basically when this is closed, that is where we will see a change in temperature. When it is open, that is where we will see that the temperature is basically it is an open source, this is a closed one, and here we will see the temperature change. Okay, this will be very useful when we will be studying the fridge. Okay, so if from a closed system, if you are continuously taking heat energy, what will happen is the temperature will go down. Okay, so we have three systems, and out of which one of them is the correct representation for the heat engine. Okay, so I will leave that to you. I request you put that in comment section and we'll talk about it more. So again, another part that we are talked about is I have represent this circle is representing with an arrow, and it is a clockwise rotation. What exactly is this clockwise rotation? That is something we need to see. Okay, so moving ahead, that can be shown with the example of steam power plant, so which is also an example of external combustion engine. So steam power plant looks something like this, and we have studied all these elements separately in the last chapter. So what we have here is boiler, turbine, condenser and pump. So we all know what does boiler do. Boiler will heat up water and convert into steam. We know that turbine will use this steam, high temperature steam, and use that steam to generate certain work. Condenser will condense this particular steam to water, and pump is nothing but to pump the water back to the boiler. So here what we are seeing is Q in is the amount of energy required for the boiler into the boiler for the water to convert from water to steam, and Q out is the amount of energy taken out of the condenser required to condense the water. Okay, though similarly we have W in is the amount of energy required to run the pump, and W out is the amount of energy done by the turbine. So here for a quick representation of this, let's have a small analysis. I have divided into 4 sections, particularly point 1. Point 1 is the inlet of boiler, point 2 is the inlet of turbine, point 3 is the inlet of condenser, and point 4 is the inlet of pump. I would like to represent this on a TS curve. Okay, so in TS curve also we will see our dome, and obviously this dome will be dividing this entire section into the known parts: liquid zone, mixture zone and the superheated zone. So let's start with point 1. So point 12 will be somewhere here in the compressed zone, liquid zone. We will have water, it is in the form of water, and when the heat is given, this is the Q heat, it will have and at a constant pressure it will reach to point 2. Okay, the steam will be generated. This is just now in the revision we have talked about it, and during this the process is going from 1 to 2, and this process we require the amount of heat in to be Q in. Okay, so from point 2 we are going to the turbine, so therefore it is shown as an isentropic process, and you must be familiar with this because it was taught in the previous chapter itself. So we are going from point 2 to point 3, and while this is happening we are generating work. So now we are at point 3, it is a saturated vapor zone, and from saturated vapor is going into the condenser and coming out as saturated liquid. So this is the process from 4 to 3, and during this we have to take the heat out of the system so that the water is getting condensed back into liquid form. So from 4 to 1 it is nothing but a process going upwards where we see the pump coming into action. So what has happened during this complete process? We started from 1, went to 2, 3, 4 and back to 1. So this has formed a complete cycle. There are 4 processes, and all these 4 processes are in a cycle. So therefore if I want to see what is the change is internal energy, so internal energy from 1 to 2 obviously there will be a change, 2 to 3 obviously there will be a change, likewise 3 to 4 and 4 to 1 there will be obvious change. But if we consider this as the entire cycle, then the internal energy change is 0. So overall cycle, for any given cycle, the internal energy change is 0. Now if you try to apply the first law, okay, so what we get is this. We say get that the work net is nothing but Q in minus Q out, because since it is a closed system and undergoing a cycle, change in internal energy is 0. Okay, This is nothing but the application of first law here. So here also we understand that what is the net work. This net work can also be given as work out, basically the work done by the turbine and the work required by the pump. So this is what we have as net work, and two equations to find it. Okay, so this, now moving ahead, we can see that all these processes are in a particular path. Okay, so if I want to draw, I can draw a clockwise rotation circle which is indicating a clockwise rotation of this particular processes. So basically, whenever now onwards, whenever you see a circle denoting such an arrow representing a heat engine or a refrigerator or pump, heat pump, we will be very careful of properly drawing this particular circle and arrow. Okay, so this clockwise rotation is indication of positive work, basically indicating we are going to get work out of this particular cycle. So I think that explains the previous that is much more to explain the cycle system of this heat engine. Okay, so moving ahead. Okay, so the remaining aspect is thermal efficiency. Like we have talked about in our thought bubble, for any given engine we need to find out what is the efficiency of this particular any given engine. So now the representation is something like this. Okay, and along with few notations: high temperature reservoir at a temperature TH which is not supposed to change, and the amount of energy taken out is QH. Okay, so here also you can see the representation of the heat engine. Okay, it is not necessarily required to be this particular set, but a clockwise rotation. Okay, so we are having a work output and certain amount of heat is reduced to the reservoir at TL, and then amount of energy released is QL. Now we are asking what is the thermal efficiency, but my question is what is basic efficiency? Most of the time whenever a student, whenever 11 12 standard students come to engineering, they talk efficiency as output upon input, whereas in engineering that is not true. You have to be very specific about what you are saying as efficiency. Efficiency is desired output upon given input. Okay, so that is efficiency, because if you simply talk about output upon input, that doesn't indicate the proper efficiency. In this case, in our case, if you are talking about the thermal efficiency, what is our efficiency, what is our desired output? Is it W net or Q loss? So our desired output is Q net. Okay, and the given input is QH. So therefore, the output of this particular heat engine can also, somebody can say okay, the output is the amount of energy released to the surrounding, but no, our desired output is work net, and the total given input is QH. Okay, so it is network output divided by total energy input. We had already seen what is the work net, which is nothing but QH minus QL, which is easily represented by this image. So therefore, using this I can rewrite the equation as Q and efficiency as W net upon QH, and using these two equations I can get 1 minus QL upon QH. Okay, so this forms my basic equation for heat engine. So here I would like to start with a small numerical, and we can wrap this up. So let's take certain time to talk about this example. So what we have here is heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of the waste heat rejection to the nearby river is 50 megawatt, determine the net power output and the thermal efficiency of the heat engine. So here again, the students, those who can solve this, I request you to pause the video and solve it on your own, and for the remaining, this is the process that we are going to do. Okay, so first of all, we should always draw the schematics, how it will look like. Okay, you have to be very specific about what you are drawing. So this is it, this is how it would something look like. So furnace is our reservoir, high temperature reservoir from which we are taking heat at 80 megawatts, and we are losing it at QL to the river, which is our low temperature is a sink basically at 50 megawatts. So as per the basic equation, what do we know? QH is nothing but W net plus QL. So what is given is QH and QL, and W net is nothing but QH minus QL, so 30 megawatts, and efficiency is as simple as that. Okay, so this was a very simple numerical. I hope it was understandable to all. So let's take another example And here let me iterate what is the question. We have a source, and from that source we have two engines, engine 1 and engine 2, and you are supposed to tell me what is the basically efficiency, which is the more efficient engine out of these two. So what is given for first input? It is given that QH is given as 100 kilojoules and Q rejected is given as 80 kilojoules, whereas for the second one work net is given as 30 kilojoules and waste heat is given as 70 kilojoules. So I hope you should be able to solve this numerical. So again, you can stop the video and take your time to solve this. I'm moving on towards the explanation. So for the first one, what we know is it's exactly like the previous numericals, 100 minus 80, so we will get the work output as 20, right? And similarly we can get here, we know that QH is nothing but the addition of work net and the waste heat, so 30 plus 70 is nothing but 100 kilojoules. So we see that same heat input for both and different work output. So obviously looking at this, it is evident that the second one is more efficient. Okay, this was a simple, very simple explanation for the heat engine, its efficiency, and cyclic processes and the cycles. Okay, so the remaining part that we have is the Planck's constant statement, heat pump, refrigerator, and applying of these principles to the various systems and more complicated systems. We'll see that in the next part of this particular video. Till then, thank you. Please put your comments in the comment section, or you can contact your respective faculties for any doubt regarding the particular subject. Thank you. Stay safe, stay home.